Welcome to this presentation. I am Dario Santonocito, a PhD student from the University of Messina. This work is entitled Experimental and Numerical Assessment of the End of the Thermoelastic Effect during Static Traction Test. The aim of these works regard the investigation of the fatigue properties of a medium carbon steel C45 adopting full-fit technique such as infrared thermography. The mechanical properties of the material were evaluated and the temperature trend of the specimen surface was monitored during tensile tests. The experimental temperature trend is compared with a numerical finite element model to assess the end of the thermoelastic effect. In this work, the static thermographic method is proposed as a rapid test procedure able to correlate the temperature trend to the fatigue properties of the material during static tensile test, adopting a very limited number of specimens. Thermography has been used as an aid for assessing the fatigue properties of several kinds of materials. As observed by La Rosa and Risitano, if we cyclically test a material with a stress above its fatigue limit, the temperature evolution of the specimen, monitored with an infrared camera, is characterized by three phases: an initial rapid increment in the first phase, then it reaches a stabilization temperature, and finally, in the third phase, a very high further temperature increment until failure. Generally, the higher the applied stress, the higher the stabilization temperature, but, on the other hand, the subtended area of the temperature number of cycle curve could be assumed constant and related to an energy parameter phi. If we report the stabilization temperature versus the applied stress, the fatigue limit of the material could be defined as the intersection with the stress axis. In addition, if we stress in a stepped way the material and we evaluate the energy parameter and the different stabilization temperature, it is possible to obtain the number of cycles at which the material will be broke if cyclically tested with that stress, hence obtaining the SN curve. The static thermographic method has been developed during the last 10 years. The first paper by Risitano and Risitano was presented in 2009. In 2013, Risitano and Risitano proposed the static thermographic method as a rapid procedure to derive the fatigue limit from a tensile test. During static tests of common engineering materials, the specimen's temperature is characterized by three phases: an initial approximately linear decrease due to the thermoelastic effect, following Lord Kelvin's law. Then, in the second phase, the temperature deviates from linearity until a minimum, and finally it experiences a very high further increment until the failure. If it is possible to estimate the stress at which the temperature trend deviates from linearity, that stress could be related to a critical microstress which is able to produce in the material irreversible microplasticity. This critical stress, the limit stress, is the same stress that, if cyclically applied to the material, will increase the microplastic area up to produce microcracks, hence fatigue failure. The relationship between the applied stress or strain and the corresponding temperature change in solid material consists of two contributions due to a thermoelastic and a thermoplastic effect. The thermoelastic effect is a well-known phenomenon adopted in stress analysis to evaluate the distribution of the first invariant stress tensor. Under adiabatic condition and for a linear isotropic homogeneous material, the variation of the material temperature follows the Lord Kelvin's law, with Km being the thermoelastic coefficient. After the material locally reaches a stress condition beyond its yielding stress, the reversible plastic deformation leads to an increase in temperature. From the first principle of thermodynamics, the rise in internal energy could be addressed to the heat generated by plastic deformation. It can be linked to the mechanical energy by means of the Taylor-Quinney coefficient, defined as the percentage of plastic deformation energy dissipated into heat. In the elastic phase, the temperature experiences a linear decrease due to the thermoelastic effect. If a plasticity condition is reached locally in some internal defect point of the material, the linear trend equation is no longer valid and the heat amount leads to a deviation from the linear trend. Static tensile tests were performed on specimens made of C45 steel with a nominal cross-section of 12 per 6 mm. The static tests were performed with a servo-hydraulic load machine MTS 810 with a stress rate equal to 400 MPa per minute, able to ensure adiabatic test conditions. The infrared camera FLIRA-40 with a sample rate of 2 Hz was adopted to monitoring the specimen's surface temperature. The tests were performed on 3 specimens. Their surfaces were coated with high emissivity black paint on one side, and the maximum temperature value of a rectangular measurement area was recorded. A nonlinear finite element model was implemented on ANSYS PDL, adopting 1/8 of the specimen geometry. The elastoplastic material behavior of C45 steel was modeled adopting a multilinear isotropic hardening plasticity model with true stress-strain data. Extra solid 186 elements were chosen, and after a calibration procedure, a number of 3,584 elements were adopted. Symmetric boundary conditions were applied to the geometry, while the tensile force was equally distributed on the grip section nodes. The first stress invariant and the plastic work per unit of volume of the cross-section area have been evaluated during the load increment. During static tensile tests, the evolution of the specimen surface temperature has been evaluated by means of an infrared camera. The applied stress is reported versus the specimen's surface temperature variation, estimated as the difference between the instantaneous temperature and the initial temperature of the surface recorded at time 0. The temperature data has been filtered with a air loss filter with a data span of 10% in order to reduce the outliers and highlight the thermoelastic trend. In the initial part of the temperature time curve, it is possible to clearly distinguish the linear trend of the temperature. Then it deviates from the linearity, reaching a plateau region. Suddenly, it experiences a rapid increment. It is possible to draw two linear regression lines, the former for the first linear phase, delta T1 fit point series, and the latter for the second phase, delta T2 fit point series. Solving the system of equations, it is possible to determine the intersection point of the two straight lines. The corresponding value of the applied stress, the limit stress, could be related to the macroscopic stress that introduces the first plasticization phenomena in the material. For the free static tensile test, an average value of 222 plus minus 4 MPa has been found for the limit stress. This value is in good agreement with other fatigue investigations of the same material made by other authors with traditional fatigue tests. In the figure, I reported the experimental superficial temperature of the specimen, not filtered, and the estimated finite element temperature versus the applied nominal stress. The experimental temperature trend experiences a deviation from the linearity of the thermoelastic effect for a stress value below the yielding stress of the material. After the yielding stress has been reached, the temperature experiences a high further increment till the specimen breakage. The finite element simulated temperature trend show a perfect linear trend up to the yielding point. Then the plastic work per unit of volume suddenly increases, leading to an abrupt positive change in temperature, reaching asymptotically the finite ultimate stress. Focusing on the first part of the temperature trend, it is evident how the experimental temperature deviates from the linearity for a nominal macroscopic stress level approximately equal to the limit stress. It is easy to distinguish the two phases, the first where both experimental and simulated temperatures show a linear trend, and the thermoelastic coefficient Km is able to properly fit it, and the second where the experimental and simulated temperature have different trends. The reason of the different temperature trends, experimental and simulated, may reside in the presence within the material of local defects that lead to local plastic condition, hence to a temperature rise. In this work, the energetic release during a tensile test on a C45 steel has been evaluated. The infrared camera allowed the application of the static thermographic method, monitoring the specimen surface temperature under adiabatic conditions. It has been possible to assess the limit stress of the material as the microscopic stress at which a deviation from the linearity of the thermoelastic effect is noticed. An elastoplastic finite element analysis has been carried out on the same specimen geometry and compared with the experimental temperature trend, showing how the presence of internal microdefect within the material leads to an increase in the temperature due to plastic deformation. Knowing the value of the limit stress from a static traction test, it is possible by means of the static thermographic method to predict the fatigue behavior of the material, even with a limited number of specimens and in a short amount of time. Thank you for your kind attention.